So for this next section, we're going to talk about the Pythagorean theorem, and then that's going to lead into our distance formula. So pretty much up to this point, we've talked about all these different operations that will undo each other. Addition and subtraction undo each other, multiplication and division. The only thing we haven't seen how to take care of is what if I have an exponent? Specifically, what if I have a 2 is my exponent? So that's our square or square operation. So the process to undo that is going to be something called a square root. So I'm going to go through the definition, but I think it'll make a lot more sense when I give you some visual examples. So a square root of a positive number x is a number you have to square to get back to x itself. So we denote this by what's called a radical. So it kind of looks like that long division symbol, but it has that foot on it. So to give you some examples, we know what the square operation does. If I take 1 squared, it means do 1 times 1. So 1 squared is 1. I'm going to just show you in the calculator as we go through stuff simultaneously. If I do 1 squared, it is 1. 2 squared is 2 times 2. So 2 squared is going to be 4. So again, just to show you on the calculator, 2 to the second power is 4. 3 squared is 3 times 3, which is 9. 4 squared is 4 times 4, 16. And 5 squared is 5 times 5, which is 25. Okay. So now I'm going to undo this operation, which means I'm going to take the square root of each of these numbers, and it's going to land me back to the number I started with that I was squaring. Okay. So going through these, for the first one, I'm going to kind of work downward, or start at the bottom and work upward. If I take the square root of 25, I'm asking myself what number times itself gives me 25. And in this case, that is 5. Okay. So the square root of 25 lands me at that base of 5. So to show you on this calculator, you have a square root button. So what I need to do is I need to type the number underneath the square root first, and then I press the square root button, and it lands me at 5. Okay. And then likewise, we can go through all of these. If I'm asking what the square root of 16 is, I'm asking what number times itself gives me 16, and that would be 4. And then the square root of 9, what number times itself gives me 9? That would be 3. And then the square root of 4, what number times itself gives me 4? And that's 2. And then likewise, the only number times itself to give me 1 is 1. Okay. So essentially what's happening here is when I take the square root of 5 squared, just square root of 25, it cancels out and gives me 5. If I take the square root of 4 squared, that's 16. The square and square root operations cancel and give me 4. Okay. So you can think of my next one would be 6 squared is 36. So the square root of 36 is going to be 6. Okay. The problem is you can kind of look at the jumps in here. All of those numbers in between aren't going to be nice. So if I try to take the square root of 17, no number times itself will give me exactly 17. That's nice. So you're getting this decimal approximation instead. Likewise, if I pick any number between 25 and 36, say I do 30. If I take the square root of that, also not nice because I don't have that solid number times itself giving me 30. So really, if you kind of list out these what we call perfect squares, you're going to see all of the perfect square roots as well. So the number after this would be 7 squared is 49. Then 8 squared is 64. Nothing in between will break down nicely as a perfect square root. Okay? But just because the number underneath isn't perfect, like I can't do the square root of 37 nicely, doesn't mean that I can't simplify it, okay? So if I look at the square root of 48, if you notice 36 and 49 are my two perfect squares it falls in between. And if I try to take the square root of 48, it gives me this decimal approximation. So what I'm going to do with my calculator is I'm going to go through and I'm going to divide it to see, can it be written in terms of 4, 9, 16, 25, 36. And then 49 is already bigger than it, so I don't need to worry about that. So if I take 48 and I divide it by 4, I do get a nice number. So this is a good first step. And then I'll show you there's actually a better way to do this, but this is a good start. So what I can do is I can write the inside as 4 times 12. And I know that I can take the square root of 4. That gives me a nice number 2. So I can break this down because it splits across multiplication. So the square root of 4 is going to be 2. So you can plug that in to double check, but square root of 4 is 2. And then we're left with the square root of 12. The problem is with this, I got to see, can I break down the 12 anymore? So going through, now I'm going to see, can I write 12 in terms of any of these numbers? But now I have less to try from because there's no point trying anything after 16 because 16 is bigger than that. So I want to see if I take 12 and I divide it by 4 again, oh, I can break 12 down even more. So this is 12, or 2 times the square root of, now I can write that as 4 times 3. And repeating the same process, we'll go up here. That gives us 2 times the square root of 4 times the square root of 3. And the square root of 4 we know is 2. So simplifying this out, it gives us 4 times the square root of 3. And now 3, there's absolutely no way to break that down anymore, so that is as far as we can possibly go. What this means, though, since I had to do this twice, I could have actually done this with one step back at the beginning. So I'm going to actually erase all of this and show you a shorter cut. So although it was divisible by 4, it really is divisible by a bigger perfect square. So again, instead, I'm going to start, 36 is the last number. That's a perfect square. That could divide into 48 because 49 is bigger than it. So there's no point in doing 48 divided by 49. So I'm going to take 48 and I'm going to try dividing it by 36. Well, not nice. That's okay. So let's try the one below it. 48 divided by 25. These both didn't work. Okay. So these are no good. Let's try the next one. Let's do 48 divided by 16. And what do you know? I get something that is nice. So it is divisible by this perfect square. So I can write the inside instead as 16 times 3. And now, like I said, that square root is going to split across multiplication. We can take the square root of 16. So I'm asking myself what number times itself gave me 16, and I know that's going to be 4. So it saves me quite a bit of time. This is equal to 4 root 3, okay? So this is a really nice operation. It's going to cancel out those squares or that 2 exponents. So the square and square root are going to cancel each other out. So this is really nice because if I have an equation that involves the square power, what I'm going to do is I'm going to take a square root to get rid of it. So let's utilize that to solve for this equation. We've got x squared plus 16 equals 25. Well, I want to get rid of this 2 power, but I'm going to do the same thing as when I was solving equations. I'm going to isolate my variable. So the first thing I actually want to do is I want to move this 16 to the other side. So that gives us x squared, and then over here we have a 9. Now to get rid of the square power, I'm going to go ahead and take a square root. So the square and square root cancel, and we get x. And then the only number times itself that gives me 9 is 3. So 3 is the solution to this equation. Now, technically, this isn't quite right. So to kind of fix this, what we really want to do is when you take a square root, you should put a plus or minus in front. And the reason for that is if I'm sitting here and trying to see what number times itself gives me positive 9, if I plug negative 3 in, it also works. Negative 3 times negative 3 is positive 9. So you actually get two solutions. You get one being positive, one being negative. However, what we're going to work with in this class in the context is realistic examples. So when I go to take the square root, I'm not going to care about the negative case because this is going to be something like a distance. A distance isn't negative. Or the side of a triangle. Side of a triangle isn't going to be negative. So for the context of us, we don't have to worry about that negative solution. But just know in general, technically you should get two answers plus n minus of that version. So one of our main applications that we're going to use the square root in is in the Pythagorean theorem. So maybe you've heard this at some point before, but if you have a right triangle, which means you have this right angle or that 90-degree angle, then there's a nice relationship between the three sides. So we'll call the two sides that form that right angle A and B, and then this longer side that's across from the right angle C. Okay, so in any right triangle, there's a nice relationship. If you take a squared plus b squared, so the two sides that form the right angle, it's going to equal c squared. So a and b form that 90-degree angle. Now these are also given different names. So the two sides that form the right angle, we call the legs of the right triangle. It's what our hypotenuse stands on. So the hypotenuse is that longest side across from the right angle. Okay. So we can utilize this. If I know two sides of a right triangle, I'm going to have one that's missing. I can solve for it and take a square root to get that missing side. So starting with this first one, the side missing is the one across from the hypotenuse. So that's our value of C. So setting up my Pythagorean theorem, my one side squared plus the other side squared is equal to that hypotenuse squared. 6 squared is 6 times 6, which is 36. 8 times 8 is 64. And C squared is unknown. So 36 plus 64 will give us 100, and that is equal to C squared. So if I want to find C, I need to take a square root to get rid of this. And again, I don't have to worry about the plus or minus because I'm just working with a side length. So the number times itself that gives me 100 is going to be 10. The square root of 100 is 10. And you can plug that into your calculator to verify if you're not good at thinking of that on the fly. So the side of our missing triangle is going to have a length of 10. Okay. In this next one, I'm missing one of the sides that forms that 90-degree angle. I have no idea what it is. You can call it A, B, C. Well, C you should reserve for the hypotenuse. You can also just call it X. Really doesn't matter how you label this. Okay. But setting this up, we go ahead and square the two sides that form the right angle, and that is going to equal the hypotenuse squared. So if you take 10 squared, 10 times 10 is 100. 13 times 13 will give you 169. So solving for x squared, we go ahead and subtract 100, and that gives us x squared is 69. So if I want just the value of x, again, we take a square root to make it cancel. And unfortunately, if you plug this into your calculator, you're going to see you get a decimal. It is not a nice number. If it doesn't say to simplify, you don't have to. So you can just say this missing side is the square root of 69. Okay. Now, the reason we're going through, it might seem a little bit strange that we're bringing back triangles, but we're actually going to need this to find our distance formula. So what I'm going to do is I'm going to try to find the distance between these 2 points, and I'm going to utilize the Pythagorean theorem. So I've gone ahead and plotted them. I want to find the points between 0, -2, and 3, 4. So we've got them 2 plotted. I'm basically looking for what is this length connecting the 2. So what I'm going to actually do is I'm going to draw in a right triangle. I'm going to go across, and I'm going to go straight down. And that's going to form that 90-degree angle. So if I can figure out the lengths of these 2 sides, then my hypotenuse is the one that's missing. So we can just do this by counting. If I go ahead and count how many spaces I'm moving over, that's 1, 2, 3. So this distance here is 3. And likewise, counting up, that's 1, 2, 3, 4, 5, 6 spaces. So this side length is 6. What I can actually do is dissect this even further, because if you look at these 2 y values, it's really just the difference between them. This is one y value minus the other. Okay. And then likewise, if I look at the difference in the x values, that's exactly the distance I'm running across. It's really the rise and the run. Okay. So this value here, change my color to match it, is one x value minus the other. Okay. So these are just the rise and the run. Okay. But now that I know these side lengths, I can go ahead and I can set up my Pythagorean theorem. So one side squared plus the other side squared is the hypotenuse squared. Okay. 3 squared is 9, and then 6 times 6 is 36. So that is my distance squared. And then 9 plus 36 is going to give me 45. So that is d squared. So to get d on its own, we go ahead and take a square root. And I'm just going to flip this. The value of d is going to be the square root of 45. Okay. And again, I'm going to show you how to simplify this because we can in this particular case. What I like to do, especially while you're doing your homework, maybe off to the side, just kind of keep a list of all of your perfect squares. So we're going to keep going until I get a number that is higher than 45. And if I go to 7 squared, it is 49. So I want to see, is 45 divisible by any of these numbers? And indeed, it is going to be divisible by 9. If you take 45 and divide it by 9, you will see it is 5. So we can actually write this as 9 times 5. And then I can take the square root of each of these, and the square root of 9 is going to be 3. So the distance between these 2 points exactly is 3 square root of 5. Okay. So you can really do this every single time, but definitely it's very tedious to have to draw this triangle. So instead, I'm going to give you the formula for the distance between 2 arbitrary points, but it comes directly from the Pythagorean theorem. So if you are ever forgetting it, draw yourself a picture. So say I have 2 points, x1, y1, x2, y2. If I set up my triangle in exactly the same way, then this side here is the rise, which is the difference in y values, and this side here is the run, which is the difference in x values. Okay. So going through our Pythagorean theorem, our hypotenuse squared is going to be one leg squared plus the other leg squared. Okay. Or you can even rearrange this, because I can go ahead and take the square root on both sides. We can say the distance is equal to the square root of the difference in x values squared plus the difference in y values squared. The one thing you really want to be careful about, number one thing that happens, is you go ahead and take the square root of each. You cannot do that. It only splits over multiplication. So just be conscientious when you're simplifying these. So let's just do two examples. We're just going to utilize the formula. We're going to find the exact distance between the 2 points. We want to simplify as much as we possibly can, and then plugging it into a calculator, we're going to approximate the distance to 2 decimal places. So starting with this first one, I'm going to go ahead and just preset up our equation. We've got to take a giant square root, difference in x values squared, difference in y values squared. Again, like the slope, makes no difference which one you'd pick to be the first. Just try to stay consistent. So we'll start with this point in that first position. X is -5, y is 2. And then in the second point, x is 0, y is 7. So from here, it's just a matter of simplifying. -5 minus 0 is -5. 2 minus 7 is also -5. So if you do -5 times -5, it is going to be positive 25. And then likewise here, positive 25. So this gives us the square root of 50. So at this point, you absolutely could plug this into a calculator to get your decimal approximation, which you should see is about 7.07. But to simplify this, I want to see, is it divisible by any of those perfect squares? So again, just going to list them out. And we'll go up to 8 squared. Because 64 is now higher than the number that's in here. So if you do 50 divided by all of these, starting with the biggest one and going downwards, 50 is divisible by 25. So you can really write this as the square root of 25 times 2. And then we're going to take the square root of each of these, which gives us 5 root 2. Okay. So that is the exact answer, fully simplified. And again, that decimal approximation, if you plug that into your calculator, you should see is about 7.07. Okay. So it's not a terrible formula to remember. It's very similar to working with our slope. Same kind of idea, just a little more intricate, but it just comes from the Pythagorean theorem. So we got one last example. Again, just going to preset up our distance. We're going to take a giant square root, difference in x values, plus difference in y values. So filling in my first point, 3 and 8, and then -1 and positive 6. So if you do 3 minus -1, that's 3 plus 1. So this will be 4 squared. And 8 minus 6 is 2. 4 squared is 16. 2 squared is 4. So the distance between these 2 points is the square root of 20. Okay. Now I'm going to bring these down just so we can see. No reason to rewrite them. Go ahead and divide 20. Really, you only have to test the numbers above this. 20 is not divisible by 16 or 9, but 20 divided by 4 is nice. So you can break this down as 4 times 5. Taking the square root of each then. Square root of 4 is going to give us 2, and square root of 5 we have to leave as is. Okay? So this is our simplified exact answer. And again, when you're plugging into your calculator, just do the square root of 20. You should see that this is about equal to 4.47. Okay? So again, just be very cautious of this. The square root will only split across multiplication, will not split across addition or subtraction. So you want to condense the inside a bunch before you try to simplify it.